Hey gang, before we dive into today's video dealing with the law of cosines, I wanted to give you your pop culture history for the day. This is a song from the band Ace of Base called The Sign. Posted up with Gang in Geometry. I'll leave the rest up to you if you want to Google it, but music video is pretty goofy. It might be an interesting way for you to recall law of sines, law of cosines. Eventually, there's a chorus throughout the song that's, I saw the sign. In this case, we're taking a look at the cosine. So not quite law of sines, we're dealing with now law of cosines. Notice the difference. So a different trig function that we're using here. What's cool about this? We can reference law of cosines when we know all three side lengths of a triangle, aka SSS, or two sides and an included angle, SAS. So this is different in comparison to the law of sines because recall, with law of sines, we would use that if we were dealing with AAS or ASA or SSA. Now we can use law of cosines if we're dealing with three sides or side angle sides specifically. This allows us to find the third side of our triangle or the missing angle measures of the triangle. I will warn you that this set of equations is a bit more challenging than the law of sines to recall. So take this moment, pause the video, consider writing down these equations, and I'll touch back in a second to give you a bit more information about what that all means. Did you pause the video? Did you copy these down? Did you copy the example down? Sure hope you did. Let's talk about what's going on here. So if we have a triangle ABC, we can let A over here, B over here, and C represent the lengths of the sides, which makes sense because they're on the outskirts. Opposite angle A, angle B, and angle C respectively. This allows us to then say that if we were to have A being squared, this is equal to B squared plus C squared. So notice this is similar to Pythagorean theorem. But now we're subtracting versions of 2B, C in red. So 2 times B times C, so times those side lengths, times the cosine of angle A, which is down here. So this would allow us to solve for that missing length of A, because if we get B, we get C, and we know angle A, we can then solve for A, the side length of A, if we just take the square root of over everything. This allows us to then create these other two where if we were solving now for B, this would get hold of A squared plus C squared, subtracting 2AC, multiplying with cosine of B. So notice that if we're solving for our side length of, let's say, A, the only time that we really see A throughout this whole equation is way out here. Whereas in between, we just deal with B and C. So that might be a way to think of it, is that whatever you're solving for, the only time that you see that letter in the uppercase is at the way end. Everything else that's in between is just the other side lengths that you're talking about in the triangle. So that may be helpful as we move forward. This is an in-depth way of looking at law of cosines. It's kind of cool if you want to pause and take a look at that, but I'll just take a look at the examples that we have here. And if at any point you wanted me to break down how this actually works with law of sines and law of cosines, just let me know. But I'm just going to focus on examples because I think that makes the most of our time together here, and you don't have to listen to me talk as much. So let's see what's going on with this. we're being asked to find the missing angles and side length in the triangle below. So let's take a look at that. So we're looking for missing angles and the side length in the triangle below. I know that if I were to look at this triangle, I'm definitely missing a few things. So let's take a closer look at that. I'm definitely missing C. I'm missing angle A, and I'm also missing angle B. Well, let's think. Is there a form of law of cosines that solves for our missing side length of C? There sure is. We can recall that C squared equals A squared plus B squared minus 2AB cosine of angle C. So that's something we could use. So let's take that further. So we know that C squared is what we're missing, and this should be equal to A squared, which is 11 squared, plus our B squared, which in this case is going to be across from angle B, so this is 5. Notice we're just dealing with side lengths here. We're then subtracting two versions of 11 times 5, and we're multiplying this with cosine of angle C, which we actually happen to know is 20. And so if we were to compute all of this, we would get a lot of numbers, and I'll just cut right down to it. This would be 121, adding on 25. You're then deducting 110 cosine of angle 20. And if this is now trying to go for C, how could I get rid of this exponent? How could we go from C squared just to C? We could definitely take a square root. So let's do that. So we can take the square root of everything that's here. If we let our calculator do the rest, try and pause the video, see if you can compute this on your own, see if you can input this correctly, how you need it. And of course, make sure that your answer is going to be in degrees. Did you pause the video? Did you try to compute this out? Let's see what we get. So in our calculator, we should have gotten something to the effect of, well, I know we're taking a square root. I know that we're squaring 11, which is 121. I know that we're going to be adding on 25, then we're subtracting 110 cosine of 20, and that should get us approximately 6.53. So that's what we can say C is. So we got that so far. But are we done the problem just because of this? Not quite yet. So let's see what else we can do. We know that C is solved for, but we still need A and we still need B. Is there an equation that, or a form of law of cosines that references an angle B or an angle A? What do you think? Well, I know that if we fall back on what we saw before, in here we see that the first equation and the second equation reference angle A and angle B. So let's use something like that. And this calculation may use a lot of space, so I'll just try to focus on what's in here. So you have some options with which one you could solve first. What's cool about law of cosines is that it's going to hold no matter which equation we use, as long as our calculations are correct. So in this case, I'm going to just pick which one. So I'll go for B. And I'll use a different setup. So I know that in this case, getting my marker, Sorry for all these delays. Okay, let's do this. So I know that I have b, which is 5. So I'll just rewrite this equation real quick. Cool. So I know b is 5. I know that a is 11. And I know that c, in this case, let's approximate it to be 6.5. And if I deduct two versions of 11 and 6.5, this would just leave me with cosine of angle B, which is what I'm looking for. Cool. So again, I could have fallen back on a squared equals b squared plus c squared minus 2 bc cosine of angle A, but I'm just using b squared because it doesn't really matter which one you use. All right. So this is going to give you some number under here. This is all a number. I think the easiest way to go about this is to just think about what needs to move to the other side and then what that's going to look like. So let's move 11 squared, 6.5 squared, and recall that this should be equal to 2 times 11 times 6.5 cosine of b. And then how can I take this further and just isolate the cosine part? What do you think? I can divide both sides by this. And I think a lot of students will get really gung-ho on computing all of these numbers. And honestly, I would hold off and just let your calculator compute everything that you need. So that would cancel this. But recall, what's this still going to be equal to? Cosine of b would be equal to all this. So how could we just take this further and solve for b? We could take cosine inverse of all this. And so let me just rope that in. This will give me some number. Yeah, that's fine. I'll leave it like there. I don't want to get too crazy with it. So if I get cosine inverse of everything that's there, that will allow me to just get a hold of what angle B is. So let's compute that real quick. Maybe pause the video and do that. Did you pause the video? Did you solve? Should be saying that angle B is going to be approximately 15.18 degrees. And then what's cool is that you can fall back on the idea that our angle should add up to 180. So we could just take 180 minus that 15.18 minus that 20. And then this will give us what angle A should be. So if you compute that real quick, angle A should be approximately 144.82 degrees. Cool. So notice we got angle A, we got angle B using cosine inverse. We could have also used law of sines right here, but I took it further just to show you another example of when law of cosines can be used. But honestly, I should have just used law of sines because I had a pretty good setup where I knew what this side was and this side was, and I had this angle, so I could have taken that further and solved for angle A. But it's all good. Still got what I needed. I hope this was helpful. If you have any questions, please let me know if I can help. Hope everybody's having